You may have learned about implicit differentiation in school today and you're a little confused. Don't worry, I'm here to help. Implicit differentiation is not actually that hard, and it's a concept where, the idea is a little more challenging to grasp than it actually is to use it. So I'll teach you the process and also teach you what's really happening behind the scenes. And I'll try my best to explain it in a very simple way. This video is part of a video series that I'm making on differential calculus, so if you're struggling with this topic in general or if you need any more help, you can go and check out the playlist as well. So let's get into implicit differentiation. First of all, I think we need to understand what's happening and why we use implicit differentiation. So the reason why we use it, right? For the most part, up until now, we were given equations or given expressions, functions that were written in terms of y and x, right? Say something like this, where one variable was completely isolated on one side, and then the rest of the equation was written in terms of another variable. So y and x were not mixed on either side, and y was isolated. It was just y on one side. And so in this case, what we usually did was differentiate using our rules, right? Differentiation rules, and this would be dy dx, or f dash x, I guess. And in the first video, I taught you that dy dx is the same notation as derivative of fx. That's what's been happening, right? But why we need implicit differentiation is because sometimes we're given equations that are written like this, where the variables are mixed in on both sides. And sure, in the beginning, you could ask, well, why don't we just rearrange the equation in terms of y or in terms of x and then derive this, right? And we would derive this for the positive, we would derive this for the negative, and figure out the derivative. But the reason is, if you're doing this, if you're rearranging all of this into an equation in terms of y, some equations, okay, some difficult equations are going to take you forever to do that, or it's just not going to be possible when it includes log and sine and cosine and all that. It's difficult, okay? And even if it's a simple equation like this, you're just adding another step that could lead to an error, or that could lead to a mark that you lose in an exam. And so you don't have to take this step, and with implicit differentiation, it becomes the whole process becomes more efficient. So this is what really is happening in implicit differentiation. I think we learn derivatives in a way that we kind of already found shortcuts, so we don't really need to see what's happening behind the scenes, and we just automatically think, okay, we have an equation written to y, we can use the rules and get this. But what's really happening, I think it's really essential to understand what's happening behind the scenes. So let's take the same equation, y equals 3x squared plus 2x, and actually expand everything out in a way that is really happening. So the first step here, if you want to derive, is actually deriving both sides in terms of x. And this is the notation for doing that. And great, now you're deriving both sides by x. And so on the right-hand side, we could do what we normally do, because we're deriving an equation or an expression written in terms of x by x. So there's no contradiction there, and it's fine. And so what would happen is you would use your rules and get the derivative on this side. But what happens on the left-hand side is a little bit more interesting. When you have the derivative of y in terms of x, you can't really do that. So we have to take another route in order to derive y and get this result, basically. What we can do is we can derive y in terms of y, and this would be the notation, right? We're deriving y in terms of dy. But if we just do this, obviously we know that this does not equal this, right? And so we would have to get from this to the initial equation. In order to do that, what you would do is multiply this whole thing by dy dx, and that way this will cancel out, this will cancel out, and ultimately this whole expression will become differentiating y to dx. Right? So all you have to do is multiply dy dx in order to get to what the original expression was. And so that's what's actually happening. And when we do this, say we're just deriving y in terms of dy, we would do that as if, it's the same thing as if you're deriving x by x. It would just, the power would come down, and then it would be x to the power of 0, so this would be 0, and it will equal to 1. And in the same way, this will also equal to 1. And so if you look at it in terms of the broader equation, in the whole thing, there's going to be a dy dx here. And so what's happening is you're multiplying 1 by dy dx, and that's why you're getting, when you take the shortcut, when you take the route that you have learned so far, you're getting the outcome of dy dx is equal to 6x plus 2. So what we've learned so far is going from this to this directly, but what's really happening behind the scenes is something like this, where you're changing the way something is derived, and then you're multiplying something to kind of balance out that change. So say we have an equation like this, the same equation here, and we want to use implicit differentiation. Well, the first step would be to just derive both sides by a given variable. It could be x, it could be y, it doesn't matter. And we have to make sure we do it to both sides, because in an equation, you got to do one thing and you got to do the other thing equally on the other side. So first of all, if we take a look at the right hand side, we're deriving anything by a constant, it'll give you a 0. And I explained that in the first video, so if you want to check that out, go ahead and do so. And then when it comes to the left hand side, we can kind of expand the expression in this way. And from here, we can say that this term, we can just derive the normal way, because we're deriving x by x. But when it comes to this, we can't really derive y by x, as we discussed just now. And there's a contradiction here. So we have to take another route in order to get here, which means we're going to have to derive y first, this y term first, by y, and then multiply the whole thing by dy dx in order to cancel things out. And so this is what's happening in implicit differentiation. And so we would derive this normally as we would if the y was replaced by x. So it would just be 2y, right? And then we would be left with dy dx is equal to 0. So the result would be, if we want to find the derivative of this, which is dy dx, we want to isolate dy dx on one side of the equation, which would give us minus x over y. So you see how much faster that was compared to when we rearrange it and derive both cases and then look at the conclusion and come up with the final answer. This is why we use implicit differentiation, and this is what's actually happening behind the scenes for implicit differentiation. If you understood that, great, but if you didn't, I'm going to go through a couple examples and just show you my thought process, not going through all these behind the step scenes, but just the way I think and just the way how I approach questions. Okay, so let's take a look at these examples. First of all, let's start with something more simple. This is really similar to what we had just now, but this is the way I would approach it. So when we have first of all, we have to identify if we want to use implicit differentiation, and we know straight away because x and y are on the same side and it's kind of just combined. So we can use implicit differentiation and say, okay, let's derive everything as if it was normal, but if the variable is not x and it's just y, what we'll do is multiply it by dy dx. So that's what's going through my head. I'm not really thinking of the behind the scenes process that I just explained. So okay, let's go ahead and do that. When we derive this, it becomes 2x. And when we try and derive this, we're like, okay, well, it's y, so I'm gonna have to derive it the normal way, but multiply dy dx right after it, and then derive the 8. And then from here, it's just rearranging to dy dx, and you would get minus 2x over 3y squared. And that would be your answer. So it's really simple. All you got to remember is that you got to multiply dy dx to whatever variable that is not x when you're deriving it. Otherwise, you just derive it the same way. Let's look at the second example here. So we're deriving the first one, say it's just 1 plus, and we're deriving this expression, right? We have to use the product rule because it's one function multiplied by another thing. So we'll use the product rule. We'll derive the first one, 2x, and it's just x, so it's fine. And then we'll write down the second one, just copy it down. Plus, we'll write down the first one, and then we'll derive the second one, and which will give you 1, but you have to multiply dy dx because you're deriving y this time. And then we would come to the last term, and that would be, again, another y. So you would need to derive it as if you would derive x, but then include a dy dx in the end. And then this becomes 0. And so if we want to rearrange it, we can rewrite the equation so that dy dx on one side, the rest the other, and then you can factorize dx, and then you can divide to get dy dx. So that's how you would approach it. You still have to apply the product rule, you still have to apply the quotient rule, you have to apply any other rule that we've learned so far. But just remember, when you're deriving something by y, when you're deriving y by x, you have to include dy dx at the end. Okay, let's look at this third example, which is a little more complicated. First term, sine y. We know how to derive sine. It becomes cosine y, right? But what did we just do? We derived y. So we need to multiply it by dy dx. The second term is, it seems like we need to use the product rule. So we'll do that. We'll derive the first one, x. We just derived x, so it's fine. And then we'll write down ey. And then we'll add, we'll write down x, and then we'll derive ey. And when we derive ey, we said that it just stays the same, but we need to write dy dx to cancel things out. And then the last term on this side is 2y, and we would derive it the same way. And we would get 2, but we would multiply dy dx. And from here, it's just, simple algebra, really. Just combining dy and dx onto one side, and then the rest of the terms on the other side. And that will be your final answer. Pause if you need to, and just read through what really happened. Basically, what I did was I moved all the terms that had a dy dx onto one side, so here. And then I moved all the other terms without the dy dx onto the other side, factorized everything by dy dx, and then divided so that I isolate dy dx on one side. And so that would be the derivative of this equation. So a little complicated. Rewind, rewatch, pause, interpret, and just consume all this information. Implicit differentiation is not hard. You just derive everything the normal way, but whenever you're met with a variable that you're not deriving by, you add that variable derived by dx. So like, if you're given y, then you put dy dx. If you have an equation, say v and x, and when you're deriving v, it wouldn't be dy dx, obviously it would be dv dx. So just keep that in mind. It's not dy dx all the time, it's whatever that variable is. That's really all you need to know about implicit differentiation. It's not that hard, it's just that extra step of adding the dy dx after you're deriving a term of y. Make sure you don't forget the rules that you've learned so far. The product rule, the quotient rule, the chain rule, you have to include all of them. But as long as you remember that implicit differentiation is not any harder than just normal differentiation. So there you go. That's how it works, and that was implicit differentiation. So I hope that helped. If you want me to make videos on other topics, then leave it in the comments below. If you have questions, you can leave it in the comments as well. I reply to every single one of them. Thanks for watching, and I will see you in the next video.